I didn't show you this slide in the last video, and I wish I had. There's a lot going on here, but this summarizes nicely what I was talking about in terms of comparing the main greenhouse gases and really, this is, I guess, is a decent video table. We're leaving out water vapor. So what I like on this one is that it has the infrared per molecule and then relative contribution. So you should know from the video before and this table which of the main greenhouse gases, water vapor, carbon dioxide, methane, and ozone, CFCs, has the strongest amount per molecule, has the strongest relative contribution, which one's the rate of increase is changing fastest, so on and so forth. So just something to keep in mind. This video is stuff that I thought you should know, but I don't like how they handle it in the book. So there's a lot of stuff in here that's not in the book, so something to keep in mind. We need to talk about a word that I've mentioned a few times but haven't defined particularly, is the word proxy. And a proxy is an indirect measure or evidence of temperature or other climate change. The two main variables that they tend to use in terms of climate proxies are temperature and then droughts. And then additionally, we can have other measures of like the composition of the atmosphere itself. So this diagram on the right-hand side of this slide shows you three of the major ones. We have tree rings, which are sort of down here, tree rings. And you've probably looked at a tree cookie, they're called, and you can see the different rings in them. We know how much trees, especially species that have been around a very long time, like pine trees and whatnot, that they grow at certain rates based on certain temperatures and other weather phenomena like drought. And we can tell both drought and temperature from these tree rings. Now, it's important to remember that a proxy, in order to be reliable, needs to be compared to the instrument record. So in terms of the good proxies that are used in science, we use ones that we can still extend into temperatures that we've been measuring since the 1880s with relatively accurate thermometers, or even the 50s, 1950s, even better. So tree rings are one that we use. And additionally, I'll talk more about ice cores, but there's also ice layering. We know that in certain climate phenomenon, in terms of drought or times of more precipitation, as well as temperature, we get different layers of the ice. And as lakes and ocean sediments, which are in this one, as well as corals. Now, corals grow at certain rates based on the temperature of the water around them. So all of these we can use to model whatever the temperature was. But that's not really the only thing they do with a proxy. It's not like they were like, all right, well, look up what the temperature says a tree ring was 100,000 years ago. What they'll do is they'll take these long-term records of all these proxies, and maybe they look like this. And then maybe there's one for ice cores that looks more like this. And if there's one for sediments that's maybe a little more jagged. Oh, let me pick a color. And they will try to find a way to match them up. And if this one, say this one at the bottom, doesn't match up well with either the instrument record or the other proxies, it will be excluded as a proxy. So there are other proxies that are out there that tend not to be used particularly. There was a proxy in snail shells that used to be used a lot, and we don't use that anymore because it's found to be unreliable. Another one I want to mention that I don't have a diagram for is pollen. I mentioned this because it's gotten a little more press lately. When they do pollen, they try to relate it to pollen is interesting because it's dispersal, like whether it's a fine layer or a thick layer, and as well as on the chemical level, like the structure of the pollen itself. Pollen will have different that endospore, whether it's a warmer year or a colder year, and it will have a different chemical composition, whether it's a drier year or a wetter year. So pollen's been used a lot lately as a proxy, and it's working out pretty well. And so all these proxies are put together along with the instrument record, and as well as direct evidence, like we're going to talk about ice cores on the next slide, as a way to look at historical climates. So that's what they mean by proxies. So this is a very bad diagram of ice core data, but the general idea is, and we saw it in the movie The Day After Tomorrow, where he kind of was in Antarctica, quote unquote, though apparently not. And basically they'll drill down into the ice sheets. And the very large ice sheets, like in Greenland and even more so in Antarctica, can go back literally hundreds of thousands of years. We used to, the longest continuous one when I was in college was only 180,000 years. But they've recently found one from Antarctica that goes back 300,000 years. So they take these ice cores and then they section them and they know which end goes with which end, A, B, line them up. And they take these back to the lab. And I've actually seen them. I tried to convince the district to take us, but they said no. To Lamont Doherty, which is right in New York. They're the most famous lab for ice cores in the United States. And they cut the cores in half. And you have this like tube of ice. And sometimes some of the ice has soot on it. Sometimes it's very white. Sometimes it's very clear. And they can look at these different bands of ice and tell what the climate was like. One of the coolest things was on a very old ice core, not ice core, ocean sediment core. They actually had this really cool sparkly line in it. And I asked them what it was. And ocean sediment cores are less reliable for direct atmospheric temperature and better for atmospheric composition. But it's really cool because that sparkly bit was iridium crystals, which were formed during the impact event that caused the KT boundary. So I always thought that was pretty cool. You can actually see the moment with like before dinosaurs and after dinosaurs. Anyway, I'm distracted by the parts I think are cool. Your book talks about the IPCC kind of a lot. There we go. And the IPCC is the Intergovernmental Panel on Climate Change. And I'm going to call it the IPCC from here on out because I hate saying the whole thing. So this is a global group of scientists, over 1,500, one of whom is literally across the street at the NOAA lab. Dr. Norb Sudi from Rutgers is on the IPCC. And they don't actually do a lot of their own research. What their main job is they look at all the research published on climate and over the since the 70s, probably going back to the 50s. And they summarize all this research because it would be impossible for any one person to read all of that research. There's hundreds and hundreds of articles published each month. And they've published 5 of these assessments, which are reviews of this literature. And each assessment is called an AR. AR stands for assessment report. So we're on the 5th one. Your book actually only talks about 4. And this is because your book was published in 2014 and it came out in 2014 and they didn't update it. This is a common issue that as soon as something is published, it's no longer accurate. And they predict climate change. These numbers, I'll show you the ones that are from the actual report itself. And each year, they take into account all this information and they revise their summation of what they think the current research shows. So AR5 was the very first AR, which was back in 1990, gave a likelihood of humans influencing climate change of only 60%. And AR5, which has taken into account, another 25-ish years of data, has upgraded the likelihood of human activity directly causing the current climate change to 90%. This was massive. I mean, if you look at the summation of research, it's, climate change is occurring and it's occurring due to people. Now, in addition to that, the IPCC, as part of their ARs, produces climate models. And they make these climate models based on carbon emission scenarios. And the scenarios tend to be, and this is one of the great uses of the IPCC, because a lot of research just tells you what they think is going to happen. And their model is their model. But the IPCC makes these models based on what they predict could happen politically. So there's 4 main models, and I have them. Let me show them to you here. There's a diagram similar in your book, but it doesn't include 4 models because they've added 4 models and a 4th model instead of the 3 they had in IR4 because I'll explain as we go. So this green line is it's the lowest one. It's called A2.16, and basically the idea here is, let me get a pen so I can draw on it. Okay. So the idea here is this one's going like this. And this one's based on the Kyoto protocols. And the idea, especially the talks that were done in France, that the amount of emissions given off is going to peak here. And if it peaks in 2020, notice it continues to increase temperature. That's because of lag. There's no getting around it. And then it comes back down. And that's the ideal scenario, what we're hoping, that carbon emissions will, even if we stop putting them out, it'll the concentration in the atmosphere will increase for a little while and then come back down, which would be nice. These other scenarios are based on different things. They tend to go by tenths. So the purple one is it peaking in 2040. The orange one is 2060. And the red one is in 2080, which, let me make sure I draw it right. And these talk about the concentrations of CO2 in the atmosphere. And the longer we wait, the later the lag gets. So these models are really important, and where we end up. Notice these endpoints. If we wait till 2080 as a global society, I mean, we're going to see CO2 concentrations that have never before been seen since life arose on this planet. 1150 would be 3 times functionally what we have now. So these are the models that are used. Now, from these concentrations, they then use all that proxy data to make predictions. So see how we have 2.6. This is the one if we stop soon. Oops. Let me go back. 2.6 means that in your lifetime, we will likely see a temperature increase of 1 degree all the way up to 1.7. And those are Celsius and Fahrenheit. But if we're looking at 8.5, goes up by 2 degrees, which doesn't sound like a huge difference, but by almost 4 degrees by 2100. So these are really big changes. Now this, I put this in here because it was in the report. There are issues with the sea level projections, and we'll talk about them more when we do, what's going to happen. But these have all been revised upwards in the last 6 months. We're seeing real issues with sea level increase. Temperature is fairly easy to do. So if you know CO2 and you can predict temperature increase fairly well, sea level rise is another level of complexity, and this tends to be exponential complexity. So this is less sure than this. This is pretty good. So I put this graph in here. This came out in 2014 as well. And this is, actually it came out in early 2015. And this is the big graph, the global temperature of the planet increase. So what they did to make this graph is they took this black line. Oh, I'm just going to go forward, go back. This black line right here, they took from 1901 to the year 2000, and they averaged that together, the average temperature of the whole planet, over those 100 years, and call that the mean. So that's the average temperature. Oh, there we go. And then they've taken each individual year and plotted it against that mean. And you would expect some to be above that number and some be below. So you can see that it was cooler in the 1880s and warmer in the 2000s. And the blue is like, the bars represent standard error. So you can kind of see that they're changing as well. So you can see there's a trend. It was cooler and then it got warmer. By the way, if you ever hear about the 70s, which would be like right in here, there was in the 1970s, people were actually afraid we were entering an ice age. And if you notice, right around there, we sort of had like a zigzag, a bunch of wiggle room around that like mean for the century. And they now think that what was going on in the 70s is before the Clean Air Act came, the U.S. and parts of Asia were putting, and Russia as well, were putting out, so much soot into the atmosphere that we were actually increasing the albedo of the entire atmosphere. So we were having a cooling effect. We couldn't even get as much light in. Anyway, so the take-home message here is that it's getting warmer. This is undeniable at this point. Even the scientific consensus is A, that it's getting warmer, and B, that it's human activity that is the most likely cause of this. I'd also like to point out something that just was published just in the last month. 2015 was the warmest year on record. And not only was it the warmest year on record, the degree to which it was warmer than all the other years is significant. Notice everything's kind of on the same line here, right? Very even. I'm going to plot 2015 off of this 100-year mean was 0.97. I would really like to draw a dot, but I'm just going to draw a line. It would be there. It was, because this is on the left axis is temperature relative to the mean. It was 0.97 degrees warmer than the mean for 1901 to 2000. So one of the concerns, people are really becoming more concerned because not only does it appear to be that it's getting warmer, but it was nice because for a while in the 2000s it looked like it had flattened out, which, hey, that's not so bad. It's a little warmer. But now it appears that it's beginning to jump again. And if you look at the other years, there was periods of flat and then jump and then jump. And that's the concern. So what we're going to do from here on out for the rest of this chapter is talk about what are the possible effects and predicted effects of climate change.